Okay with that? Okay. Same thing here. Make sure it's in the proper form. Remember, the proper form means not just one quadratic and one constant, but the quadratic is naked and alone on the left, and the constant's alone on the right. So I go check. I have a quadratic and a constant. Check. Quadratic on the left, constant on the right. Check. But my quadratic's not naked and alone. Oh, what am I doing there? So, nope. Because I divided it away, I'm not pulling out GCF. I'm not factoring this. Right. X squared equals 12. No. See, this is not pulling out GCF. This is just, dividing every term by the same thing. I'm not factoring it. I'm not saving that 3. Making a lone quadratic on the left, constant on the right. Ready to apply. Twelve is not a perfect square, but it does contain a perfect square factor pair. Which means I can root and release the left, and there's a leftover bit that stays trapped. Okay with us? Slide this up. We're still kind of pulling that out. Parentheses make a difference. Now we have a binomial squared. If we just had a free-floating linear term, we could use this method. This isn't a free-floating linear term. It's a quantity squared, a binomial squared, and a constant. And we definitely don't even have to ask ourselves if we can factor that. Because in order to know that, we'd have to first square this out and combine like terms, and why go through all that mess? Got a positive radicand, so there's no I. These are real solutions. Real irrational, but real, not non-real. Can I simplify that at all? No, nothing to simplify, so I can go ahead and finish. Now I have to finish, unlike those first two examples, I have to finish solving for x. So I'm going to add 4 to both sides. Now, very important, remember, anything on the right-hand side, when you're simplifying that radical, anything to the right of that plus minus stays to the right of that plus minus. Whatever can be done to simplify this, like here, 2 square root of 3. Here was a plus, but everything stays to that right of that plus minus. So there's a negative and a positive. Okay. Anything on the left-hand side is going to stay. We're going to move it over the equal sign, but it's going to stay to the left of the plus minus. A common careless mistake is to make this 4 times square root of 5. No. Anything you move over from the left stays on the left. This is going to be 4 plus square root of 5, not times. The radical in its simplification stays to the right. Anything moved over from the left stays on the left of the plus minus sign. So it'll be positive 4 plus minus radical 5. Or 4 minus radical 5, 4 plus radical 5. First thing you're going to do if you have a negative radicand. Second thing is ask, well, can I keep going on what's left? Not a perfect square, but now this is two terms on top. I also sometimes refer to it technically mathematically as a two-headed fraction. If you can factor out something on top, is there a common factor of negative 3 and 2? Of 3 and 2? No. So there's nothing you can do to simplify that. If you could factor something out from the top and then it reduced with the 4 on the bottom, you may be able to simplify some. Now that's technically mathematically how you do it. This is how we did it in chapter 10. If we had to fully factor before we could cross out. Okay? If you have rationals, fully factor and then cross out factors. So I could factor out something from the 3 and the 2. The radical doesn't count, or the I, okay? But this is just like the two coefficients. Factor something out, and then if it, I could cancel it out with that 4 on the bottom. I find it, that's why it works mathematically. I find it more efficient and less messy, less easy to lose track of what you're doing, by thinking of this as a two-headed fraction. It's two-headed because it's got a plus or a minus here. So here's one head, here's the other head, and they have a common body, a common denominator of 4. You can reduce a two-headed fraction. You can reduce a fraction if you can divide the top and the bottom by the same thing, right? With a two-headed fraction, you can reduce it if you can divide both the heads and the body by the same thing. Okay? So if you're reducing 2/4, well, both 2 and 4 are divisible by 2, so it reduces to 1/2. If you're reducing a two-headed fraction, you've got to know, is there a GCF of 3, 2, and 4? And there's not, but if there were, whatever that number is, you could divide all three of them by that same number. Now that might not, there might still be like another number you could take out of 2 of them, but no, you have to be fair. It has to be all 3 parts, both heads and the denominator, in order for you to simplify it. And we're going to see an example. This is done. We're going to see example. That's going to come up again a little bit later. Now you could put this in complex number form. Okay? Negative 3/4 minus 2 squared is 7 over 4, I, a plus bi, and then 2 over 4 would reduce to 1 over 2. And then the same thing with the minus. This is fine. You can stop here as far as I'm concerned. I'm not asking for you to put these in a plus bi form. Now, if you did, if you're so inspired, I might get a bonus point for that because I'd be really impressed. But you don't have to get full credit. So this would be negative 3 minus 2i radical 7 over 4. And the negative 3 is negative 3 in both of them. It's just one's minus then and one's plus 2i radical 7 over 4.
What you say the extra point?
Because it has an I, and not all of these will end up having I's. This one does, which means it's a complex number, a non-real complex number. And the formal notation for a complex number, a non-real complex number, is a plus bi. And when we were dividing in chapter 11.7, we get down to you have to put it in a plus bi form, which means if you had a two-headed fraction, you had to share that denominator with each part to separate them. So you had an a and you had a bi, and then reduce them separately. So if you did, that's basically this thing. If there's an I, you can give the 4 to the first part and the 4 to the second part with a minus in between and a plus in between, and then simplify both to have a plus bi form. Okay? I'm not requiring, the directions will not say put in a plus bi form. If you come across one that is a non-real, and you want to go ahead and do that, it's not wrong. In fact, like I said, it would probably impress me. It might be an extra point. Okay? but not required. You can stop here, but you do want to make sure that there is no common factor with those three numbers, and then you're done. Move on. Okay. Now, I don't like to waste trees, but I want things to not be scrunched up, so this is the square root property study page with 4 examples, and I'm going to move to a fresh page now. Okay. Good, from our third method. Okay. So this is where we left off last time, was with the completing the square method. Okay. So we're going to run down the steps and then practice a couple more. We were rushed at the end there. So our third method is to solve by completing the square. And this is also in 12.1. And this is a method that when you first see it, because it's really kind of foreign to everything else we've been doing, can be really intimidating looking at first. I'm going to keep these problems really basic. You can get really complex with these, but I'm going to keep them very basic. I want you to get really used to the steps and find a comfort level with them. Okay? But I am going to show you an example that does involve fractions, because that's something you may see moving in college algebra, and I just don't want it to be a surprise. But the ones I'm going to ask you to do on the exam for regular credit are going to be very basic. Okay? So I want you to be comfortable with this idea, with the concept behind it, because this skill is not going away. It's going to come back in different contexts multiple times in college algebra. All right, so when do you use it? Okay. You use it when you have a quadratic trinomial equation. So it's a trinomial, meaning it has a linear term, unlike the ones we just did with only a quadratic and a constant. This is a trinomial, so it's a quadratic, a linear, and a constant. And so that is specific. That is the form ax squared plus bx plus c. This is a quadratic trinomial equation, so it's got a quadratic, full-on 3, quadratic, linear, and constant, and then just a pure standard form, just to, not that that's the form we need, but that's algebraically how you write a quadratic trinomial equation. Okay? Where a is the quadratic coefficient, b is the linear coefficient, and c is the constant. And that is not factorable. And again, you can actually use this even if it is factorable. It's just kind of overkill to use this. If it's factorable, factor it. Okay? Especially since the best time to use this is when you have a equal 1. So if you've got an a equal 1 trinomial, factor that. Okay? If it is. If it's not factorable, if you can't find that magic pair of numbers, if it's prime, what we called prime before, then this is a great time to use it if. You can use it on any quadratic trinomial equation. However, the best choice, if you're making choices, if you're given a choice of what to use, and it's just totally up to you, then this is the best choice, this is the best thing to use if a equals 1 and b is even. If a is not, well, you have to have a naked x squared. You have to have a equal 1. So if your x squared is not naked, you have to divide away your a. And that creates fractions most of the time. If your b is odd, remember we find our magic c in this one by dividing by 2 and then squaring it. So if your b is odd, then you're going to have a fraction. If it's even, then you'll have a nice magic c that's not a fraction. Okay? So avoiding these is ways to avoid fractions. Okay? And this is mostly what I'm going to give you this time. I might have one with an odd b as a bonus, okay? And so that you're not surprised when you see it in college algebra. Okay? I'm not really going to give you any that have a not equal to 1, okay? But I want that to not be a surprise. You can still use this method. You just have to divide that away first. Okay? So the setup. Very important setup. If you do not set things up for this the way that you're asked to for each method, you will not get the correct answer. The setup looks like this, algebraically and then in words. So algebraically, you have a naked x squared. So if there was an a, you divided it away first. And then you have your bx. So you have your linear term, your quadratic term and your linear term, both of your variable terms. And then you're going to leave a space, and it's always going to be plus. Because remember, we're working with a perfect square trinomial. And a perfect square trinomial factors into a binomial squared, a binomial times itself. And if you multiply out a binomial times itself, it's either going to be 2 pluses or 2 minuses. This is always positive. If you FOIL out a binomial times itself, the last term is always positive, 2 pluses or 2 minuses. Okay? And then it's equal to, now I'm going to use something I didn't use last time. I'm going to use the letter K. K is an alternate way to write constant. You see that a lot in college algebra too. The reason I'm using K is because if there was, the C that was over here is not going to work for us. We need a new C that will make a perfect square trinomial. So whatever constant we had here, we pushed over here. And it's still a constant. We're just going to call it K now because it's not the C that we needed. Okay? And because we're adding something, in order to create our perfect square trinomial, we're adding something here, that magic C, but we have to keep the scale balanced and we have to add the same thing to the other side. So the setup is variable terms on the left. Let me put it out in words. So both variable terms on the left-hand side, LHS, okay, and a constant, which we're calling K now, constant K on the right-hand side. Okay. That make sense? I don't want to confuse anything with a K. It just means you moved your number over. Okay, so you're not in standard form for this. Okay. So, your steps. First step. If if A is not equal to 1, then you divide all terms by A. Okay, you're going to divide it away from every term. Like I said, I'm not going to give you ones like this. I just don't want you to be surprised. You can use them, and if you encounter them moving forward, that has to be the first step. If you don't do that, it's not going to work. You have to have a naked x squared, or this won't work. Okay? So, then you put in the above form with your variable terms on the left and the old constant pushed over to the right. Okay. Then, you've got to find that C. So that C didn't work. That's why you pushed it over here, and we'll call it K now. You need to find the C that will work. You find the C that will create a perfect square trinomial. Okay. And it's going to create that perfect square trinomial on the left-hand side. Okay. So once you find that C, you add it to both sides. Now, a perfect square trinomial, not just any quadratic trinomial, but a perfect square trinomial always has this relationship between its B and its C. If it does not have the relationship between its B and its C, then it's not a perfect square trinomial. And the relationship is that the C of a perfect square trinomial is equal to half of the B squared. Okay. If your C and B don't have that relationship where your C is half of the B squared, it's a trinomial, but it's not a perfect square trinomial. And we want to make a perfect square trinomial, so we have to find that magic C that will make that happen. That's why we push the K out of the way, and now we're going to add that C to both sides. Okay. Now that means you just created a perfect square trinomial on the left, so you factor that left-hand side, which is now a perfect square trinomial, into its binomial squared. The factored form of a perfect square trinomial is a binomial squared. Then you're going to have a binomial squared on the left and a constant on the right. So at this point now you solve using the square root property. So now you solve for x using the square root property. Those steps in that order. Okay, so does the concept of this make sense? You're understanding all the terms I'm using? Sort of the reasoning for what we're creating? Okay. I'm going to put 2 examples here and then 2 more. So examples So this is where we left off, sort of introducing this and now practicing a few of them. So if we had x squared minus 2x equals 2. Now see, it's a equal 1, but if I just take a glance at these numbers, even before I put it in standard form, I can see it's not going to be factorable. Okay? The more you practice, the more you start to recognize that. Okay? So this is it's got an even b and an a equal 1, but it's not factorable. So it's perfect time to use the completing the square. Now I've got my variable terms on the left, and I got the constant on the right, so it's in the proper form. But I'm going to go ahead and rewrite it and leave some space because I want to keep my scale balanced. So I've got that on the left, and I'm going to add a magic c, and I've got my other constant, my k on the right, and whatever I add is going to have to balance that out. So that's c. In order for this to be a perfect square trinomial, then this number has to be half of this one squared. Now you can put negative 2, because your b technically is negative 2, but regardless, it's going to get squared, so regardless, it's going to be positive. Okay? So I'll put it just to be really consistent. I mean, that is a b of negative 2. That gives you negative 1 in parentheses squared. And of course, any number, negative or positive, if it's squared, then it is positive. So add that to both sides. You do not have to test if this is a perfect square trinomial like we did back in 9.1 through 9.3. It was like, oh, perfect square, this is a perfect square if I have my AB doubled. Oh, yeah, it is. You don't have to test this. You know it is because you just made it. You just created that relationship that made it 1. So factoring into a binomial squared, all it is the first term. You'll unsquare the first term, and because it's a naked x squared, it's always going to be x. The middle term, the number doesn't matter. It just tells you whether it's going to be plus or minus. And the last term, unsquare. 1 squared unsquared is. Okay. So unsquare the front and the back, and the middle term tells you plus or minus. Binomial squared is equal to 3. Know what to do from there, right? Can't be simplified, so I finish it off solving for x. Actually, I'm going to do just horizontal examples, so I'll put the 3 on the back. I want to point out real quick that this does have numerical meaning. You don't obviously, I mean, like, it's not as obvious as a number like 2 or negative 8. But this is a real number. It's irrational, but it's real. As a reminder, this is going to be the concept we finish up with. So to start to plant that seed, when you solve an equation, any equation, whether it's linear, cubic, or quadratic, you get the solution or solutions, you get your x's, you solve for x. What does that x mean on the related 2-variable equation? This is a 1-variable equation you can solve for x. If you had the related 2-variable equation of this and you graphed it, what would this mean? A quadratic, what would it make a picture of?
Parabola.
Right. Linear equation makes a line, a parabola, a quadratic makes a parabola, cubic makes a swoop. Okay? So this is going to make this is a single variable you can solve. The related 2-variable would graph as a parabola. When you're solving the 1-variable version of it and you get your x's, what do those x's tell you about the parabola?
That's where that 2 cross, isn't it where that line, the 2 goes into? Because it's equal to 2?
It's equal to 1 plus square root of 3.
What would be the intercept?
The intercept, yes, the x-intercept, right? The parabola is going to cross. It comes down and crosses the x-axis and comes back up and crosses an x-axis. That's why you have 2 solutions. These are your two x-intercepts of that parabola. Okay? You're like, but that's ugly. That's actually a number. If you put it in your calculator, even though it's irrational, you can approximate it. So if you put in 1 minus square root of 3, that is approximately negative 0.73. Approximately negative 3/4. And that is the point on the x-axis, negative 3/4, where this parabola will cross. The other place this parabola will cross is at 1 plus square root of 3, which is approximately 2.7, approximately 2 3/4. Okay? So this is a parabola that would come down and cross at negative 3/4 and then come back up and cross at 2 3/4 on the x-axis. Okay? A very important concept. What you're solving for are x-intercepts. As you get more into functions and graphing those two variable functions, this, solving the one variable equation, will tell you so much about that graph. Two very important points for graphing it is knowing what the x-intercepts are. And even with an irrational solution, you can get an approximation of where it should fall. Okay? In fact, if I go to y equals and put in this, and I've got to put it in standard form because it's solved for y, and I'm saying y equals 0, and when y equals 0, that means I have my x-intercepts. So y equals x squared minus 2x, and then I'm going to have to move this over, so minus 2 to equal 0. So now instead of equal 0, it's equal to y, which means the solutions will be my x-intercept. And when I graph it, there's the parabola. It goes through approximately negative 3/4 and approximately 2 3/4. And that's the relationship. So that's where we're going to come back full circle. We'll revisit that towards the end as we look at our last method. Okay. So let's do a couple more examples and then introduce our last method. All right. So completing the square with these examples. X squared plus 6x plus 13. And x squared plus 10x minus 27. Now these are given to you in standard form. So remember, of course, if you're going to complete the square, these are not factorable. Spoiler alert. So even though they're a equal 1, if you crunch the numbers, if you did your ACB real quick, you say, oh, there's no magic pair of numbers. Before we'd say that time, but here we say, oh, we can still solve it, we just can't factor it, solve by factoring. All right? But a equal 1 and b is even in both of these, so perfect time to complete the square. You move forward. Don't wait to just copy down what I do. You move forward, and then I will follow behind, and you can look up and check. But try it yourself. Okay? Feel free to help each other or ask me for if you need help. But you know how different it is when you go home and do this alone on homework. So you want to try and transition that in class. Let me see how much you can do of these examples without looking at it.